Welcome 10th graders. I am so excited to have you here for this explainer. If you're tackling your Chapter 1 chemistry curriculum right now, you are in the exact right place. Today, we're going to demystify a totally foundational concept, how we mathematically represent chemical reactions. Look, as a STEM educator, I see students get intimidated by these equations all the time. But I promise you, by the time we wrap up, you're not going to see them as confusing math problems anymore. You'll see them as a beautiful, logical story. Let's get started.
Okay, so you already know chemistry is happening all around us, right? I mean, we've all seen the vibrant colors, the bubbling flasks, that crazy dynamic energy of a lab experiment. We watch these physical changes happen right before our eyes, like a gas explosion or a sudden color shift in a beaker. But as scientists, we can't just write down, hey, stuff fizzed and turned blue. We need to expertly translate those real-world physical changes onto paper. We literally need to capture that bubbling flask in a way that anyone, anywhere, can understand exactly what just happened.
So, here's our roadmap for today's explainer. First, the language of chemistry. Second, the anatomy of an equation. Third, transitioning to formulas. Fourth, the universal scientific shorthand. And finally, skeletal versus balanced equations.
All right, let's jump straight into Section 1, the language of chemistry.
Now, imagine writing out a chemical reaction like this. Hydrogen gas reacts with oxygen gas to produce water vapor at high temperature. I mean, that is incredibly tedious. Just imagine your thumbs trying to text that out during a fast-paced lab. If we actually used long paragraphs to describe basic reactions, our lab notebooks would be completely full before lunch. So instead, a chemical equation gives us this elegant, universally understood solution. H2 plus O2 gives us H2O. Boom! It's incredibly concise, it cuts out all the extra noise, and gives us exactly what we need to know.
Moving right along to Section 2, Anatomy of an Equation.
Just like an English sentence, chemical equations have a very strict logical structure, and it's built on three core components. First up are starting materials, which we call reactants. These guys always sit on the left-hand side, or LHS, and if there's more than one, we just separate them with a plus sign. Then, right in the middle, we have the arrow. Now, this isn't just a random dash. It's a yield arrow acting as a direction indicator. It shows the actual flow of the reaction, pointing from what we started with straight toward what we're making. And finally, sitting at the point of the arrow on the right-hand side, or RHS, are our products. These are the brand new substances formed by our reaction.
So for our very first translation, we're going to strip away all those extra English words and create what's called a word equation. Think about that classic 10th grade lab where you burn a magnesium ribbon. Instead of writing a whole paragraph about it, we concisely list our metal and gas reactants, magnesium plus oxygen. Then we drop in our yield arrow, pointing directly to our solid product, magnesium oxide. It's cleaner, it's clearer, and it firmly parks our starting materials on the left and our new product on the right.
Okay, Section 3, Transitioning to Formulas.
So here's the really crucial point. By swapping out those bulky chemical names for exact scientific symbols, our word equation magically transforms into this sleek, efficient formula equation. Step 1 is the word equation. Hydrogen plus oxygen yields water. Simple enough. But in Step 2, we bring in our elemental symbols. We know hydrogen gas is H2 and oxygen gas is O2, right? So by Step 3, we've got our final formula equation. H2 plus O2 yields H2O. It takes up a fraction of the space, but it actually gives us way more scientific information about the molecules involved.
Which brings us perfectly to Section 4, the universal scientific shorthand.
You see, formulas offer absolutely unmatched scientific precision, and they create a true universal language. This is mainly due to three huge benefits. First, conciseness. You get immediate visual recognition. Second, science totally doesn't care what native language you speak. A student in India, Japan, or Brazil is reading that exact same H2O equation without a single language barrier. It's standard worldwide. And third, scientific precision. Writing H2O tells us exactly how many atoms of each element are in that molecule. The word water completely fails to do that. And honestly, that is exactly why the golden rule is to always use chemical formulas instead of word formulas.
And finally, Section 5, Skeletal versus Balanced Equations.
Now, a skeletal equation just shows the basic framework. It's kind of like a baking recipe that completely forgets to tell you how many eggs to use. It gives you the reaction pattern, but it might actually be breaking the laws of physics. If we write Mg plus O2 yields MgO, well, our mathematical scale is tipping. It's unstable because we have 2 oxygen atoms on the left, but only 1 on the right. A balanced equation, though, that guarantees stability. By adding coefficients, turning it into 2Mg plus O2 yields 2MgO, we make absolutely sure we have 2 magnesiums and 2 oxygens on both sides. The scale is perfectly balanced, and it's mathematically accurate.
I really want to pause on this concept for a second because it is the absolute bedrock of everything you're going to do in chemistry from here on out. Balancing isn't just some busy work your teacher assigns to make your life harder, I promise. It honors a massive rule discovered over 200 years ago, the law of conservation of mass. This law strictly dictates that no atoms can ever be lost or created in a chemical reaction. The mass of the reactants absolutely must equal the mass of the products. If you start with 2 oxygen atoms, you have to end with 2 oxygen atoms. They just don't vanish into thin air.
To wrap things up today, keep these key rules right at your fingertips. Think of chemical equations as your most efficient scientific shorthand. Always use formulas for precision, and remember you literally must balance your equations to obey the fundamental laws of physics. Mastering this, it doesn't just get you through Chapter 1, it unlocks the entire global language of science. So now you've got the tools to translate the totally chaotic physical world into beautiful, balanced mathematical truths. Whether it's the rusting of your bicycle, the digestion of the lunch you just ate, or a space shuttle launching into orbit, it all comes down to balanced atoms. So, what real-world chemical reaction are you going to decode and balance next? Keep practicing, keep balancing those atoms, and I will see you in the next explainer.